Here we are with the final section for Chapter 7, 7.5, Quantitative Chemical Analysis. As always, you'll see the learning objectives listed. Please pause the video for a moment and copy those in your notes. In this last section, we're going to take a minute to show all of the stoichiometric relationships that we've gone through with regards to different chemical reactions and the quantitative analysis of those, and show some real-world application with some titration, some gravimetric data, and some combustion reactions. So you get a chance to work through a lot of the same work that we've already been doing and the relationships that we've already been looking at, but see how it is applied in more of a real-world setting. When we refer to quantitative analysis, you can see the definition here: determination of the amount or concentration of a substance in a sample. So again, we're talking about real world, real life scenarios here where we would isolate these in a lab setting, but we can also do the calculations along the way, and that's what we're going to work on here. Titration is the first type. We will really talk a lot about titration when we get to acid-base chemistry a little bit later, but you can see some important terms listed here. You have the titrant and the analyte. So the known concentration of one reactant, and then the other reactant is what we're trying to find the concentration of. So an unknown amount or concentration. We actually have a little online titration lab that we're going to work through, so you'll get a better understanding of the setup for this in that exercise. So I'm not going to get into that in a lot of detail right now. I would like to quickly talk about the distinction between a couple terms that are somewhat interchangeable, but there is a distinction between the two, and that's equivalence point versus endpoint. So the idea here is, in a titration reaction, there's going to be a point that we reach where the concentrations of our two substances are the same, our acid and our base are the same, and we get that neutralization. If we use an indicator to show us that color change, what we're finding there is the end point. The equivalence point is the point in the titration process where the chemical reaction in the titration mixture ends. That's the equivalence point. And so that's the point where the analyte has completely reacted with the titrant. While they'll be close, it's not exactly the same thing. So let's take a look here at a quick problem for a titration. Okay, here's an example problem. Again, so all of our, so much of what we've done so far leading up to this point comes into play in this example problem that we see here. Okay, the endpoint means, again, that the amount of our acid and the amount of our base, our analyte and our titrant, are the same, so have the equal number of moles. Okay, so things to remember here as I get into this problem: molarity, if you recall, is moles per liter. So that will be important for us here because we're obviously trying to determine the molarity of the HCl. Okay, so let's start with what we know here, and that is the information we know is the NaOH, the titrant. Okay, so because we have the volume and the molarity of that titrant, we can use those values to get to moles of HCl using the stoichiometry that we've been doing here. So let's start with the 35.23 milliliters. We're first going to convert milliliters of NaOH actually to liters. So a quick metric conversion here, because molarity again is in moles per liter. So even though the volume was recorded in milliliters, we need to make sure we get that in liters. So just a quick conversion there. Okay, now from there, we are going to convert from liters of the sodium hydroxide to moles. And they gave me that molarity. So that basically, if you recall, molarity is moles per liter. So that's that 0.250 molarity NaOH is 0.250 moles over 1 liter. Here is our, because I have a balanced equation, Here is our mole conversion, which allows me to convert from moles of NaOH to moles of HCl using the coefficients in the balanced equation. You can see that's a 1-to-1 ratio. And so my answer here, after doing this work, I will have successfully converted to moles of HCl, and we get 8.81 times 10 to the negative 3 mole of HCl. Now we're just going to use our molarity formula. What is the molarity of HCl? So molarity would equal the moles we just calculated stoichiometrically divided by the volume of the solution. And we said it's a 50 milliliter sample. Again, milliliters needs to be in liters. I could do that conversion, but I'm just going to quickly move the decimal point because I know that's liters. And we get our final molarity of our HCl. Let's look now at a gravimetric analysis. You can see here by definition, this is where we're going to get separation from the components. Here we're going to be dealing with masses and precipitates. This is mostly happens in a precipitation reaction. So instead of looking for the molarity, we're going to be looking for the mass percent. You remember when we talked about concentrations, concentrations can be recorded in a couple different ways. So typically here we're going to be trying to calculate the mass percent. Here's our example problem. Okay, so where do we start here? We're actually going to start with we're going to do our stoichiometry having started with this gram value of BaSO4 because that's the resulting in the precipitation of BaSO4. So that's the solid we've isolated. Okay, so I'm going to do my stoichiometry starting right there with that value. Okay, so we know we need to, that value is given to us in grams. Obviously, if we're talking about stoichiometry, we have our balanced equation there. Then we know we need to be working in moles. So we're going to convert to moles of the barium sulfate. If I do a quick calculation for the molar mass, I get 233.43. Next comes our molar ratio, where we're going to determine or convert to the substance the question's asking about. What is the concentration of MgSO4? Okay, so in this molar ratio step, we're going to convert to moles of the magnesium sulfate. Again, balanced equation is given to us, so I can plug in the coefficients there in my molar ratio. It's a 1-to-1 ratio. And finally, I will convert from mole of MgSO4 to grams. Again, obviously we know mole to gram conversion. I need a molar mass. So if I calculated that, 120.37. Here I get the mass of MgSO4 that we started with. And we need to, ultimately the question is, what is the concentration mass percent, since I'm dealing with solids here. Okay, so that, if you recall, mass percent equals the mass of the part over the total mass. So that would be grams of MgSO4 over the total mass of the solid mixture containing MgSO4, which was this value right here, and that is 0.4550 grams. Okay, again, times 100 to make it a percentage, and we get 69.91% as the mass percent of MgSO4 in our solid mixture. Finally, the last type of quantitative analysis that we're going to take a look at are combustion reactions. So you can take a look here of what happens. So just to refresh our memory, if I have a hydrocarbon and a combustion reaction would look like some hydrocarbon plus oxygen yields CO2 and water. So we would have that generic reaction for any hydrocarbon combustion. Let me just fix this quickly. So some combination of carbon and hydrogen is heated with oxygen, and we get the products of CO2 and water. You remember these from balancing equations because obviously we have some work to do to balance our carbons and hydrogens every time this happens. The way this analysis, I've included a diagram here of how this analysis would go. We see our sample is heated, and then the gases, which include the carbon dioxide and the oxygen and water and other things, pass through these condensers, and those gases are absorbed by some substance, and there's some example substances there as it passes our way through, which that means then we can determine how much H2O and how much CO2 is produced. If I have those values, then using my stoichiometry, I can determine the ratio of carbon and hydrogen. So let's take a look at what that problem would look like. We are given a mass of CO2 and a mass of H2O. Obviously, we are first and foremost converting to moles. Our molar mass for CO2 would go there. Once I've converted to moles for both the carbon dioxide and the water, we know that we can use our formula to go from moles of CO2 to moles of carbon. So the amount of CO2 is going to help us get that mole of carbon. And then, of course, CO2, there's 1 mole of carbon for every 1 mole of CO2. And we get a value for moles of carbon in this particular amount of CO2. We'll do the same thing here for the H2O. So the H2O will help us get our moles of hydrogen. So we will go mole of H2O to mole of hydrogen. And here it's a 2 to 1, 2 moles of hydrogen in every 1 mole of H2O. And we get our moles of hydrogen. At this point, we just want to see the ratio here, right? Because that's what we're trying to determine, the ratio of carbon and hydrogen to get the empirical formula of our hydrocarbon, the CXHY. What are those two values? How many carbons do I have? How many hydrogens do I have, right? So at this point, I'm just going to look and see what the ratio is. Mole of hydrogen to mole of carbon. So 1.79 times 10 to the negative fourth mole of hydrogen over 8.95 times 10 to the negative fifth mole of carbon. And you'll see when I do that, I'm going to get an answer of 2. So that tells me 2 mole of hydrogen per every 1 mole of carbon. And that means our empirical formula here in this problem, the hydrocarbon we had was CH2. That's the hydrocarbon we would end up with based on the amount of carbon dioxide and the amount of water that was collected in this combustion analysis. Okay, that wraps up not just section 5 for chapter 7, but chapter 7 in its entirety. So we've seen many stoichiometry problems and practices of all different types. So we'll continue to work through this and get lots of practice here as we head towards our exam.